Okay, 1.6, polynomial functions with end behavior. Again, this is something that I covered in my class, so this should look a little bit more familiar to you. However, if you're new to this, again, end behavior is actually not all that difficult. There's just very specific ways on how it gets written. So make sure you're writing it down and paying attention as we go. Okay, so end behavior is the behavior of a function, and it describes how the function behaves as it moves infinitely to the left and the right. So basically, as it's going towards positive infinity for the x, or as it's going towards negative infinity for the x. So left and right. Okay. And when we're talking about the behavior, we're talking about what is the y, right? Or the f of x doing. Okay. So remember, please, f of x is y. Okay. The end behavior is, again, what happens to the values of f of x, or the y, as x increases or decreases without bound. So this is guaranteeing, we have arrows on the graph, and increasing would be going toward positive infinity, and decreasing would be going toward negative infinity, which again, increasing would be to the right, and decreasing would be to the left when you're talking about the graph. So it's asking where the ends of the graph are going, okay? There's very, very specific ways that we write this, so I need to make sure you're paying attention. These are called limits, okay? And again, with my students, as far as for polynomials and rationals, we talked about this. We did not do separate end and or right and left bounds as far as limits. So this is going to be a little bit new as far as how it's written. So it makes sense if you read it. When we talked about limits before, it was the same thing as end behavior. The limit of f of x, so basically what is y doing as x goes toward negative infinity, right? So that's basically as it's going to the left. The way you would read it, as the x values decrease without bound, they're going toward negative infinity, right? The y values of the f of x are doing whatever they're doing, okay? And when you're talking about a polynomial, that means they're either going to positive or negative infinity, right, as well. When we were doing the rationals, remember that they were going towards their horizontal asymptotes a lot of the time. So this is the first time that we've actually talked about writing a limit notation, right, with a negative or a positive infinity to differentiate between the two. Okay, so verbally and using notation. Okay, so left side verbally, that's over here. Okay, and so in words, and again, this is something you'll be expected to be able to write. So as the x values decrease without bound, right, that means they're going to the left. They're going toward negative infinity. The y values increase without bound. Okay, so what does that mean in actual limit statements? Okay, so as a limit statement. Sorry, I forgot the word first. Okay, so the limit of f of x, and what f of x is whatever your function is, as x goes toward negative infinity is infinity. That's basically what that means, that as the x values are going more and more to the left, going towards negative infinity, the y values are going up to positive infinity. Okay, so the right, again, we're looking at this function right here, the right-hand side. Okay, in words, as the x values increase without bound, because you're going to the right, that means it's going to positive infinity for the x. What is the y value doing? The y value is going down to negative infinity. That means it is decreasing. Okay, so in a limit statement, okay, so the limit of the function as x goes to positive infinity is negative infinity. That's where the graph is going. Again, it's very, very similar to an end behavior. That's basically what it means. We call it a limit. Again, you'll get into this more when you get into calculus. It's basically just a directional statement of what's happening to the graph. It gets a little bit more interesting when we start talking about rational functions because you end up with holes in the function, right? And we have these other things that we deal with where the limits from the left and the right are not the same, going towards the same number. So it's a whole big thing. But right now we're just practicing how to write it. Okay, so that's an odd function, right? Because, 1, 2, 3, that's an odd function. This one's an even function because both ends are pointing in the same direction. Okay, so the left, verbally again, as the x decreases without bounds, the y value increases without bounds. You could also say that the y values increase without bounds if you want to put the plural in the other way. It actually does mean the same thing. So either way actually works as far as for the English of writing the statement. Okay, how we write it, again, the limit of the function as x goes toward negative infinity is positive infinity. Okay, and then the right side is also going up. So the only thing that changes between these two is as the x increases, without bound, the y values increase without bound. And again, you're going to get basically the same thing on polynomials. If they're odd, one's up, one's down. And if they're even, both are up or both are down, one or the other. Okay, so the limit of the function as x approaches positive infinity, and no, you do not have to put the little plus there to differentiate that minus, that minus on the negative one basically does the same thing. Okay, equals infinity. Okay, so again, basic limit statement for end behavior. Not too bad. Again, it'll get more interesting when we start talking about rational functions. There's all kinds of things that we can talk about, but for right now, this is basically how we're doing end behavior and how we write it. Okay, so basically using that information, we're going to draw a polynomial. Now, the degree of the polynomial is entirely up to you within the limits of if both the left and the right-hand sides are going in the same direction, then you know it needs to be even. Right? So you could make an even could be a 2, it could be a 4, it could be a 6, however many you want to do. If you have like this one is going in either direction, one's going to the positive, one's going to the negative, then you know it's an odd function. And again, odd functions could be linear, cubic, to the 5th power, whatever you want to do. Basic sketch. All right? So it's just a question of being able to read it. So this says that as x is going to negative infinity, the y is going down, and x is positive infinity, the y is going down. Basic function. Since both sides are going down, you could literally draw this as a parabola. If you want to do it as something more and you want to give it more curves, that's fine. You could do that and then go down. Those would both be considered an appropriate function as far as a sketch. Basically, what you're realizing is that this must be an even function. All right, so the other side. The left side, when x is negative, the y is also going towards negative, so that's basically down here. And as x is going to the positive, y is going to the positive, that's here. And again, I could make this linear, I could make it cubic, I could make it bounce as many times as I want, as long as the left side's going down, according to this statement, and the right side is going up. Okay, so when you are looking at a polynomial, whether it is graphed or you're doing it based on leading coefficient and all that other good stuff, which leading coefficient does tell you about end behavior, it's easier if you do the right or positive side first, only because for this reason. Okay, so the right side, oh, there's missing words, goes in the, weird. Oh, never mind. That's for the left side. Never mind. Okay, so the right side goes to infinity if the leading coefficient is positive, period. You haven't flipped the graph over. Think of it like a positive linear function. Okay, it goes to negative infinity if the leading coefficient is negative. Again, because every odd function behaves like a linear function, right? Okay, so again, that would be that way. So the right side is going down if the leading coefficient is negative. It's going up if it's a positive. And this actually works even for even functions, right? This would be an odd function. An even function, if your leading coefficient is positive, well, the right side is going to go up. And if it's a negative, then an even function, the right side is going to go down. Okay? The left side, okay, goes in the same direction as the right side if the degree is even, and it goes in the opposite direction if the degree is odd. Literally. And again, the way I normally tell everybody to remember is that all odd functions like end behavior behave like linear, and all even functions behave like parabolas, as far as end behavior. Both sides up, both sides down. All right, so based on end behavior, or based on, rather, leading coefficient and degree, we're going to actually talk about the end behavior. Okay, so this is a positive leading coefficient and an odd degree. So positive and odd is going to look like this. So the left side is going to go, so as x goes toward negative infinity, y is going to go towards negative infinity. Right side, as x goes towards positive infinity, y goes toward positive infinity. Okay, so again, positive, even. Okay, positive, even. Both sides up, field goal, right there. Or, yeah, or it's good, I guess, for a touchdown. Isn't that the same thing? No, maybe not. Anyway, I know the refs put up both arms for that one, basically signifying that it's good. Okay, so as x goes to negative infinity, y is going to go to positive infinity. And as x goes to positive infinity on the right-hand side, y is also going towards positive infinity. Again, just based on leading coefficient and degree, period. All right, leading coefficient is negative, and that is an even degree. That means both sides go down, no matter how many curves are in between them. Okay, so as x goes to negative, y goes to negative. As x goes toward positive, y goes toward positive. Or negative, excuse me. Negative infinity, since they're both going down. Okay, and remember we talked about this before, about when your function is not written in the correct form, right? Because your leading term, right, should be the one with the highest degree. So this technically should be written as negative x to the fifth plus 3, which means it has a negative leading coefficient and, oh, sorry, that's a 5, x to the fifth, yes, and an odd degree. So negative and odd, again, it's like a negative linear equation. All right, so as x goes to negative infinity, y goes to positive. As x goes to positive infinity, y goes to negative. Again, just based on leading coefficient and degree. Again, also not written in the correct form. So the first term is actually the negative x to the fifth, and then 8x squared because it's positive, and then the 4. Okay, so yeah, make sure you're catching your signs. So again, negative and odd. That means it's the exact same thing as D. Not going to write it again. Okay, this one might be a little bit trickier. So I'm just going to show you a really quick way to find your leading coefficient and your degree. Okay, so 2x times x minus 1, this is technically supposed to be negative x plus 6. Just multiply the first terms. So 2x times x times negative x is going to give me negative 2x to the third. And then that's all we need, that first term, right? So it's negative and odd. So it also is the same as D and D. So you should have D written the same thing for both E and F. All right, so almost done. Okay, so limit statements, again, it's the same thing as the end behavior. We're just going to write it as a limit this time, based on the same information. Negative, even. So I know it looks like that as far as the ends. Okay, so the limit of the function as x goes to negative infinity is infinity. The limit of the function as x goes towards positive infinity, and again, you don't have to put the plus, is also infinity. It means the same exact thing as what we just wrote on the other ones. All right, and this is positive and odd. So that means, looks like that, right side up, left side down. All right, so the limit of the function as x goes to negative infinity is negative infinity. And the limit of the function as x goes toward positive infinity is positive infinity. And that's the only difference between writing it as end behavior, which you've been doing technically since Algebra 1, and writing it as a limit statement. Okay, we are going to do example 5 in class together, just so we can get it on the graphing calculators that we're using. Other than that, we are done.